Okay, illustrative math, unit 2, lesson 24 is called Polynomial Identities, part 2. So our goal, I can justify why identities are true, and if you didn't watch my other video, an identity is an equation, and an equation which is true for all values of the variable in it. All right, so let's do this. I already did a little bit of this to kind of speed things up a little bit, but here's some instructions to make a right triangle. So it says choose two integers. So I chose 3 and 4. Make one side length equal to the sum of the squares of the two integers. So I took 3 squared plus 4 squared and I got 25. Okay. So if I can erase that and mark that a little bit cleaner. All right. Make one side length equal to the difference of the squares of the two integers. So 4 squared minus 3 squared is 7. And then make one side length equal to twice the product of the two integers. So there we go. I multiply those, double it, and I get 24. I do the same thing here. I did two different integers. I did 5 and 8. I squared them and added them together, squared them and subtracted them. Notice I had to put the bigger number up front to subtract because I didn't want a negative side on a triangle. And then I multiplied the product of the two over here on the third one. Now, I also want you to notice that the first one ends up being the biggest, okay? So the largest is the sum of the two squares, and it worked for both of them. So follow these instructions to make a few different triangles. I did 2 of them. Do you think the instructions always produce a right triangle? I guess, I don't know. I mean, I'd have to maybe measure out a stick that has a length of 25, a stick that has a length of 7, and 24, and piece them together and see how they fit. If it looked like a right triangle, I'd say yes. But maybe we can use some algebra. So let's do this. These are instructions before. So I want to use a and b for the two integers and write expressions for the 3 side lengths, okay? So if I use a and b for my two integers, the sum of the two squares, a squared plus b squared, the difference of the two squares, and then 1 equal to twice the product of the two integers, so 2ab, right? So there's the first part. So why do they make a right triangle? So if you remember Pythagorean's theorem, it's a squared plus b squared equals c squared, and c is always the hypotenuse. So remember on the last slide, I told you to look at these, how this one is the largest here, the first one with the sum of the squares. Same thing over here. So that makes me know that this is kind of like my c, okay? So if I plug this into the Pythagorean's theorem for c, and then this would have to be, one of these would have to be a, and then this would be, I'll just make it 2ab, square the whole thing. Let's see if I can use algebra and get this to equal that. So on the right side, if you need to use a box to multiply, a squared b squared times a squared b squared, I get a to the 4th, a squared b squared, a squared b squared, and then b to the 4th. So the whole thing equals a to the 4th plus 2 a squared b squared plus b to the 4th. I come over here, same thing. I need to make a box. I get b to the 4th negative a squared b squared negative a squared b squared. And this becomes a positive a to the 4th. So when I write that all out, I get b to the 4th minus 2 a squared b squared plus a to the 4th. And then when I square this is going to be, I have to square the 2, so that becomes a 4. Square the a, square the b, okay? So then when I do a little algebra here, if I start moving things around, these a to the 4th end up canceling on both sides. Same thing here if I try to move the b to the 4th over here. Those cancel. And then these are actually like terms right here. So negative 2 plus 4 would be 2. And so I just combine those like terms. And the only thing left on the right is the 2a squared b squared. So they are equal. So your answer is, I use some algebra and I would say yes, they're always going to be a right triangle because I plugged them into Pythagorean's theorem because I know Pythagorean's theorem is for right triangles. Okay. All right, so here's a list of equations. Circle all the equations that are identities. Be prepared to explain your reasoning. So we're going to try to use some algebra to get them to equal. So is a equal to negative a? Only if a is 0. If a is 3, 3 is not equal to negative 3. I don't think there's any algebra I could do. If a equals 8, 8 is not equal to negative 8. So this one's going to be a no. Let's go over here to 2. So algebra, I could multiply this out. So make a box, AB, AB, A squared, AB, AB, B squared. Add those together, so I would get A squared plus 2AB plus B squared. And that's equal to what I had over here. So since I got this side equal to this side, this would be an identity. I would say yes. So no matter what I plugged in for A and B, both sides will always be equal. All right, same thing over here. Let's multiply this out. I'll make a little neater box here to multiply. So A minus B times A minus B. So this would be A squared, negative AB, and then this would be positive B squared because negative times a negative. So this side would be A squared minus 2AB plus B squared. And that's equal to that. So I would say yes. So over here, I'll tell you what, instead of doing the box, if you want to use the box, fine. I'm going to just kind of do it in my head. A times A is A squared. A times negative B. Actually, this is the same thing as this, isn't it? This is A minus B squared is the same as A minus B times A minus B. So I already kind of did a box over there, so I'm just going to rewrite my answer. So they're not equal. So this one will be a no. There's nothing else I can do either to get them to match up. All right, let's go over here. Let's multiply this out. So I'll put my A and my B here. So this will give me A cubed. This will give me A squared B. This will give me negative A squared B. This will give me negative A B squared. This will give me positive AB squared, and this will give me B cubed. So when I look here, these two cancel out, and these two cancel out because they're like terms. This is supposed to be a 2. So these are gone, and so are these because they add up to 0. So I get A cubed plus B cubed. So that is not going to be equal to A cubed minus B cubed. There might be a few values for A and B where it would work out and be equal, but if I can't algebraically get the two expressions to be equal, then I would say no. All right, so let's go over here. So A minus B cubed. So it's A minus B times A minus B times A minus B. So I got to do all that algebra and see if I can get it over here to match up with that. Ugh. Well, luckily, I already kind of did these two. If I go up here, I already did that. So it's really going to be a squared minus 2ab plus b squared times a minus b. Let's multiply that all out. I'm going to make a box here. I'll put the, oh shoot, what did I do? Put the binomial on the left here, a minus b. Put the trinomial up top. Multiply it out. So I do all that work. Start looking for like terms here, a cubed. These two would give me -3. A squared b. These two will give me a +3. I'm sorry, not a squared, it'd be a b squared and then minus b cubed. So I want to know, is that equal to this? So I have a cubed negative b cubed. If I distribute this, I'm going to get a -3a squared b. And then when I come over here, I'm going to get a -3ab squared. So my a cubed, good. Negative b cubed, yes. -3a squared b will be right here. And then a +3ab squared. And then this was a -3ab squared. So I'm going to say no on this one. All right, and then the last one here. Oh boy, this is kind of crazy. If you look at this, these are actually a common factor. So if I pull out an a minus b to the fourth, I'm left with an a squared. Or you can think of them as like terms. We can add these coefficients here, so it becomes a squared plus -b squared. Over here. Not much I can do, but I'll tell you what, this is a difference of squares, so could I factor this into a minus b, a plus b? And then, oh, check it out. Now I really have a minus b to a power of 5. Whoops, I'm sorry, that was a minus b, not 5. And I got them to match up, so I would say check. And that one's a yes. Okay. So some of these got a little crazy. Oh, this one was a no. I said it, but I didn't write it. All right. So do a little algebra, a little multiplying. All right, next one. In ancient Egypt, all non-unit fractions were represented as a sum of distinct unit fractions. For example, 4/9 would have been written as 1/3 plus 1/9. So not 1/9 plus 1/9 plus 1/9 plus 1/9 or any other form with the same unit fraction used more than once. Let's look at some different ways we can write 2/15 as a sum of distinct unit fractions. So 2/d is 1/d, 1/2d, 1/3d, 1/6d. So we're going to use this formula to rewrite the fraction 2/15. So my d is going to be 15. So I'm going to say 2/15 because that's the formula there. 1/15. 1/2 times 15 is 30. 1/3 times 15 would be 45. 1/60 would be 90. So show that it's an identity. So I guess I would have to take my calculator here and add all this up and show that 2 over 15 equals 2 over 15. All right, another way to rewrite fractions of the form 2 over d is given by this identity. 2 over d equals 1 over d plus 1 over d plus 1 plus 1 over d times d plus 1. So let's do that. Let's rewrite it. So 2 over 15 equals 1 over 15 plus 1 over, so 15 plus 1 would be 16. 1 over 15 times 16. Okay, so now we're going to have to do a little simplifying. Let's do a little math here. 15 times 16 is 240. So I'm going to add those together. 1/15 plus 1/16 plus 1 over 240. And sure enough, I got 2 over 15. So it looks like it checks out. All right. All right. So lesson synthesis. Let's look back at different identities you've investigated so far. Pick one that you found interesting and write a few sentences explaining why. So I'm going to go with the Pythagorean theorem: a squared plus b squared equals c squared. Why is that interesting? I should just say that I find it interesting that the side lengths for any right triangle can be plugged into this formula, and the left side will be equal to the right. It's just kind of crazy that, like, let's say I draw a right triangle here. Okay, and let's change the side so it's not, if I take a right triangle here and I measure this side, and measure this side, if I plug them in, the two short ones for A and B, long one for C, it's just kind of crazy that it will always work. Anything else is just algebra. Some of the other ones that were real basic, like you had like A minus B times A plus B, that always equals A squared minus B squared. You can multiply these out in a box and you'll always get that. So, they just look differently. But all right, so is this an identity? Explain or show your reasoning. So same thing we've been doing. We're going to multiply this out and see if it equals what we got on the right. So I'm going to put A and B, A squared negative AB. B squared, A times A squared is A cubed. B times A squared is A squared B. Negative A squared B. Negative AB squared. AB squared, and then this is B cubed. So these are 0. Those are gone, and so are these because they add up to 0. So I end up getting this whole thing is A cubed plus B cubed. It looks like it's equal to the right side. All right, if I move the right side down, this was the left side, I transformed it to there, looks equal. I'd say yes. All right. Hope you enjoyed this lesson, and thank you for watching.